Assalamu alaikum. Engineer Muhammad Walid here. So today I'm going to be discuss about the seismic load case. I will give you the simple example through which you can easily determine your massive structure by manually. Actually, basically the SAP users who is basically use the SAP now can design. Let's suppose they have normally two options. They either want to calculate the load manually or by the SAP. Okay, SAP, from the SAP there is his own factors, that is importance factors, modification factors, and seismic response factor, eccentricity, we can say the ratio, and there is of the CT, that is called time period. Okay, so there is different types of thing what you can get according to your code. Okay, so I am here taking my code is UBC code UBC 97. Okay, so for the seismic load analysis, you have to give the load in two directions, that is EQX and EQY. Okay, because your earthquake or wind load or any type of load, because seismic analysis included your wind load, your earthquake load, or your fluid pressure, any type of pressure that is occur in the horizontal direction or in the vertical direction. Okay, so I will give you today a little example through which you can make a massive structure. Okay, about the seismic load analysis. So I have designed a simple sample for you, so that you can make understand that what is basically seismic load analysis. Okay, whenever you design the major building, that is elevation. Okay, this is your x-axis, this is y-axis, and this one is your z-axis. Okay, that is your height. The each story height is normally, you can see that 3.5, 3.5, 3.5, 3.5, 3.5. Okay, now this line, you can see this line, this is normally contour. Okay, this line is that line, this is normally below the earth, and normally that is the thing that is below the earth, or that of the, you will never find the seismic load or seismic analysis for that, that is normally below the earth. Okay, so for here I'm going to design this 4-story building. You have to make understand that is lumped masses, that is seismic load calculation for story building Deir Ismail Khan in UBC code 97. Okay, so here that is you have, there are different types of method you can find out the seismic load analysis. First of all, you can drop this line. This one is a horizontal line. You cannot take the whole story height. That is the story is 3.5. Okay, you have to take this half you have to lump into this, then this half, and then add these two both, then lumped into this, that is this half, then lumped into this half lumped into this, and this half then lumped into this. Okay, this portion will only be remaining up to the top roof. Okay, this is lumped basically young forces. Here I'm going to design only up to this up to this. Okay, our structure. Now this is normally I am taking the structure, and I have considered that is normally symmetrical. So what I mean that it is symmetrical, let's suppose this is our if we say that there is no basement consists, that is the ground floor. Okay, so if we say that there is ground floor, you can also make for the seismic basement. Okay, if you can name for, if you are considered for the basement, then you can name it at the seismic basement. As here I am going to discuss it for the ground floor. So here that is office. Now I am considering that up to 4th floor, which means that this level there is office, up to this floor there is library, there is classroom, there is guest room, there is store, restroom, stake. But on the side you may find out there are different types of drawings. Let's suppose you have a ground floor have different design, and first floor have a different design. Let's suppose there is office on the first floor, there may be something other thing, everything. Your code will show you that what about the thing you have, and you have to calculate the weight. Okay, now here seismic load calculation manually for 4-story building Deir Ismail Khan UBC. So first of all, you have to understand that what is basically what is base shear. What is base shear? Okay, so base shear is actually it is a maximum lateral force that will occur due to the seismic ground motion, okay, at the base of the structure, okay. So it can be occur on the base of the structure, and lateral force basically shows that that of the force that is normally acting into the horizontal direction with reference to the plane, okay. This is a now what kind of thing that is horizontal forces can be at let's suppose if I say that that uh, if you open this, that what kind of horizontal forces acting on this included. So let's suppose this one is your structure as I made there. So this is forces having the wind, okay, that is wind load. Wind load can also be included into the your seismic structure. So if there is earthquake due to which it caused some deflection, okay, seismic weight, okay, that is due to the free vibration or stored drift. This is earthquake is the second case, okay. So we can say that that second thing is earthquake, that is also a seismic ground motion due to the seismic analysis. And third one is the your basically fluid weight. Your fluid weight is also includes there are three major things that normally includes into the building. So due to the wind load, if there is high building, then to resist this we normally provide shear walls, and shear wall is normally provided at to the basement in order to resist the lateral load of the adjacent side. Lateral load is also called the basically is also a live load that normally occur parallel to the ground, okay. It is lateral load, and lateral load is basically shows you about the your live load. Now base shear, here I will increase its size so you can see it easily. It is the maximum lateral force that will occur due to seismic ground motion, okay. It's actually lateral force which will occur due to seismic ground motion at the base of the structure, okay, at the base of the structure, okay. So keep in mind that it is a maximum lateral force that is normally occur on the base of the structure to resist the lateral force, okay. This one, this is actually definition for the base shear. Now coming to our drawing, if I came to our drawing here, okay, you will see here that this one represent column, this one column, this one beam, that is beam, that is beam. And here I normally show this that that is auditorium, and here I provide normally how much that is shear wall, okay. I normally provide here shear wall and shear wall here because the wind load that is normally occur on there on it, so it normally resists easily, okay. Shear wall is actually that all the forces is normally parallel to the other thing, okay. That is normally you call it shear wall. And here is normally we provide here shear wall also in x direction. This is your secondary beam, okay. What is the difference between your primary beam and the secondary beam? Primary beam basically lies from column to column, okay. This one is column and this one is other column, so this one is lies, this is called your primary beam, and the beam which is normally lies onto the other beam, that is called secondary beam. That is from beam to beam. Always remember that that is depth to width ratio of your secondary beam is always less than the primary beam, okay. Otherwise if you greater it, then you can see there that it will and here is no support, then it will cause the deflection here due to its higher weight, okay. Must remember that this point. So I am going to start my calculation. First of all, what I am going to calculate it here. You will see here that office. Now here I am going to open my first of all I am going to open my ASC code. I am my building code of Pakistan, okay. That is UBC 97. Here you can see when you come here and drag down here, and you will come here at 526. Go to the up here, you will find here Now this is, you will see here that this is something of points before going to design the building. Okay, now here you will see that design base share, the total design base share in given shall be determined by the following formula. So this is normally your CV. What is CV? It is normally shows that this is basically seismic coefficient. What is seismic coefficient? That is normally find out from your zone factor. Okay, that is your zone factor. You will calculate from your zone factor. Okay, that is our zone factor. That I am making the building from the Deir Ismail Khan, then I will take this factor. Now what is basically I base? I is basically your importance factor. Okay, you will give different for different things. What is R? R is basically you are you can say that it is a response modification factor. There is two types of building. One is SMRF and other is IMRF. Okay, so SMRF is actually that building that which give the detail about the ductility. Okay, it is also moment resisting frame. OMRF is also a moment resisting frame, but it is does not give any detail about the ductility. What is ductility? Ductility is actually that when you apply the force on the material, then how much it has the ability to deform. Okay, that is normally that how much the material is ductile. As you know that grade 60 steel we use because that have good ductility. Okay, because it is not brittle, because brittle can break very soon when it has applied the load on it. It is not, does not bend, and it has doesn't have any ductility. T is basically your time period. Okay, you can calculate it from different method. Here the method you have given here. Okay, this is for the building for reinforced concrete, that is a moment resisting frame. Okay, MRF. Okay, you can see that reinforced concrete moment resisting frame, essentially braced frame, and for other building you have calculate from this very easily. But if we are construction our concrete masonry, then we will apply this value. Okay, 0.0743. Okay, and for the FPS, that is called the foot pound second, we have to apply 0.1. Okay, but we will work in the meter, so we will apply it here this one. First of all, in this topic into the UBC, we will also check about the total design base share need not exceed the following. Okay, so the value we will calculate from this this will not exceed from this value. Okay, that is WW, which is basically called your seismic dead load. Okay, always remember that before going to join anything, you have to find out the self weight, that is self dead weight of your slab, that is normally lies here. Okay, you have to find the dead load of beams, that beam. You have to find the dead load of the self weight of the column. Okay, then you have to apply the live load here. Okay, what is live load? Live load, that is normally movable. Okay, that is called live load. Other thing, that is the other some people take that the factors. Okay, like seismic factor normally take the live load, but that is not the live load, that is normally that of the thing. So always remember that your environmental load always taken not as a live load, because it is normally your environmental load. Okay, so it is not considered as a live load, but it is considered as a dead load. Okay, live load, whereas when any human, like when they go up and go down, like anything, you go and you place that thing onto the top, and that is removable, that is normally called as live load. Okay, here there is column, that is here we have give the dimension is 600 × 600 mm. Okay, for whereas for the FPS you can give the other value for the unit weight. Okay, here I am using meter, because of my code normally given everything in kilonewton per meter. Okay, that is PSF, but it is difficult and some confusing to convert it into PSF. So this is your office use, this is library, this is library, this is library, and this one is your slab. Okay, first of all, so what is basically your first step you have to find out? We are going to find out, first of all, this is your given slab. Okay, this one is all your slab. You have to find out the slab. Okay, so for the slab you have to take this mid. Okay, this one is the mid, because your slab is normally lie here. You have to take here and here and here, and all you will take your slab. Okay. So first of all, for taking the slab, you have to find out there is normally two things. Okay, before the slab. Okay, uh, you can now you can see here that is normally length, and this one your width. Okay, so leave this room. I will consider after. First of all, you have to take two things, that is one and that is two, that is length and that is normally width. Now this is how much this is normally taken as 4 meter. I have already told you that this section is normally in feet. If you measure the dimension, that is normally in feet, but I am considering the feet into meter. Okay, as this is just example to make you understand that how we will apply the seismic load manually. Here you will see that this is office, this is library, this is classroom, this is room, this is strike room, this is assembly room. Okay, so that is in x direction, that is 1 2 3 4 5 and 6. Okay, that is normally 6 room having 1 2 3 4 and 5 having with the same dimension. Okay, can you see here? So 5 having same dimension. So first of all, right here, for the seismic load, we have to find here first of all some of the three things, that is seismic weight calculation. Second thing we will calculate, that is base shear calculation. And the third thing what we will calculate is the seismic weight calculation. Okay, that is seismic weight calculation, and the other thing is seismic weight. Okay, that is two things we will find out here. That is two things. That is okay. Control start automatically. That is okay. I'm comfortable with this. Now I will find out what is basically about perimeters. So first of all, any type of drawing you have given, you first of all must come here and you have to find out the perimeter first. So how much perimeter we have given, that is one is column, this one is column. Okay, and other thing is your slab, this one is your slab, and third one is that is beneath the column there is walls, that is three things, and there is something other thing, that is column, that is walls. Okay, column, walls, consider it. Other thing is slab. Okay, this is slab is also, and third one is beams. Okay, this one is also considered. Now parameters, what is parameters, you can write here, that is slab. Second thing is beams. Third thing is columns. Fourth thing is walls. Okay, this one is walls. So here that is parameters. Okay, there is wall, so is further divided into two things, that is shear wall, walls and shear wall. Okay, shear wall, columns, beams, and secondary one. Okay, this one, and slab. Okay, that is slab. Okay, so that is the parameters we have to find out the given dead load of this. It is very important to find out the dead load according to the UBC code 97. Okay, so first of all, I am going to find out the slab as it is slab. Okay, then I'm going to get size into color. Okay, first of all I will, okay. So for the slab, you open it and you have to first of all make focus that there is normally how much base. So what is base? This is grids. Okay, this one is grid, this one is grid, this one. Okay, this line is normally shows you about grid. This is grid, this is also a grid, this is your other grid, this is your other grid. Okay, so always remember that grid is normally lies. Okay, so you can say that what is basically grid. So always remember that grid is always lies in the in the two center of the column. Okay, that is beam, that is normally the center to center distance between the two columns. You can say that center to center distance between the two columns. Okay, this is your normally shows as the grid. Okay, and other thing, that is the box that you will show, that show you that this one, this and this. Okay, this one is the box. This is not a box. This, in the engineering language, you can call it bay. Okay, this one is all is called bay. So how many bays here? That is 1 bay, that is 2 bay, that is 3 bay, that is 4 bay, 5 bays, and 6 bay, and that is 7. Okay, so how much bays having same dimension, okay, 1 bay, 2 bay, 3 bay, 4 bay, and 5 bay. Okay, 5 bay having the same direction. Come here, slab. Okay, first of all, you have to find out the area of slab. Okay, so for the area of slab, we have to find out that how many bays. That is 1 bay, 2 bay, 3 bay, 4 bay, and 5 bay. Okay, there is normally given about the 5 bay. 5 bay, and what is the length? That is 4 meter. This is 4, 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 and this one is 6. Okay, so you can write here 5 multiplied by 4, because number of bays are 4. 1, 2, 3, 4, 5, and having then 4. Okay, so 5 cross 4. We can close the bracket here. You can close the bracket here. 5 plus 4 plus, that is 1 bay, 6 meter. Okay, you can see here, that is overall 1, that is normally 6. So you can plus use here 6. Okay, so how much you get? That is 5 cross 4. You can open your calculator. I'm opening my calculator here. So you can see here, that is 5 cross 4, that is 20, and plus 6. So you will find here 26. Okay, you will find is 26. 26. Okay, that is in length. 26. That is, we can say that area of slab. We can say that's length. Okay, that is 26. Now one thing you here, you can say that while the other slab, you can see it, other slab having area width equal to how many bays? 1, 2, 3, and how many numbers? That is 3. So we can write as W equal to 4 cross 3. Always remember that whenever you use SAP 2000, then you have to only give the unit weight, okay, of the brick. What is unit weight of the brick? That is, if you want to load of any story building, let's suppose I am going to find out the load, wall load of this story building. Okay, then you have to find out that is 19.2. That is unit weight of the brick. Okay, then multiply by thickness. Okay, when you multiply with the thickness, then you don't have to give any length, because not any length, because SAP is considered itself as just kilonewton per meter. So kilonewton per meter, it will take per meter length as its own. Okay, you have to give their height. Okay, so into the SAP height and minus depth of the beam. Okay, that is for the calculation of the SAP. Okay, if you want to find out the parapet, then 19.2 multiply by thickness of the wall and height of the parapet. Okay, it is up to you, because it is something different, as the UBC code 97 says that for the storage you have to detect the 25%, and whereas for the area having more than 150 square meter, having 150 more than square foot, then you have to apply on the following formula. But in the UBC code 97, we normally detect 25% load, not more than this. Okay, whereas IS code 2002, that is Indian code, it says that that whatever you have the load that is more than 3 kilonewton as given into the live load table, then you will detect that about the 50% load. Whereas the UBC code says that if there is the code, you have to apply the 25%. Okay, so area of the slab is L is equal to 5 cross 4, okay, plus 4, that is with 4 is equal to 3, that is, we can say that 12. 12. Okay, so this one is the calculation of from here to here. Okay, that is from here to here, here to here. Okay, so what normally I found here. Now total, how much total we get? we get the area of the slab. You can see that area of slab into length into AS, small area of slab. Okay, so what is basically width? Width we can say here that is width 4 plus 3, so we can write here 26, that is 26 multiplied by 12. Okay, that is 312. Okay, 312, that is slab 1. You can say that slab 1. Now for slab 2, you can give that area, that is square meter. Okay, it is square power, where is the power, where is, you can say that square meter. Okay, now for the slab 2, now let's suppose if you are finding out for the slab 2, then you have to take this one, that is 10, and this one is 10.5. Okay, 10 and width equal to 10.5. so how much you get? Total 10 multiplied by 10.5. Okay, so 105. 105 this one plus. Okay, so total that is 312, and 312 this one. So how much you get? That is normally 417 meter square. Okay, meter square. That is normally, you can say that that it is 417 meter square occur. So this is this is method 2. Okay, you can say that that is method 1. Method 1 to find slab. Okay, this is method 1. Okay, so you can find out by this very easily. How you can find out the area of slab with the method 2. Okay, you can find out the area of the slab with method 2 like this. Sorry, there is something wrong with my mouse. So you can say that area. Okay, area. So here you can see that that's for this one. Click on the other. Click on the other. This one. Okay, has been the mid. This one. Okay, this one. In the middle, this one. Okay, this one. So this one. This one. Okay, you have to click here. This one. Click here. This one. 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 As this one. Now when you click on enter, then you will see here that it gives normally a square foot. As I show you that it is drawing in normally in foot, but I consider it in meter. Okay, so we can say that it is normally equal to the 417.266, that is square meter. Okay, having this one is square inch. Okay, now when you compare it with this, you have get the same as you are going to find out. Now this is our calculation for the slab. Okay, if there is any factor for your roof life, then you can also take here, but first of all you have to find out the slab. There is no load intensity about the roof here. Okay, now the second things I have to take that is normally we have to consider my beams. Okay, now multiply my beam. So first of all, before finding out the beam, you have to find that what is basically area of beam. Okay, we have to find out the beam in two direction. Okay, because it is normally in y direction, this is normally in x direction. Okay, so because in the y direction, if earthquake came from here, okay, this one, that is normally resist by this and normally occurred by this direction, that is normally directed by your x direction. Okay, so how many beams can be resist on your x direction? That is 1 2 3 4 5 6. Okay, that is 7 8 9 10 11. Okay, that is 12, that is 13 14 15 16 17. Okay, 18 19 20 21 22. Okay, and this one. Okay, and this one, this is your beam. Okay, always remember that this is not including in your beam, this is your secondary beam. You have to calculate for this individually. So for the office here, whereas I am calculating for my office here, and that is a beam. That is how many beam having the having same dimension. First of all, I have to calculate some of the thing very first. As you see here that our all dimension, that is normally 4 meter. Okay, and here I have column. I am going to first of all open the statement. So the second thing is this, that someone take the slab load area, that is normally we can say that internal area. Okay, you can also take the area from to the beam. Okay, someone take the slab of the area, that is from here to here. Okay, then this one area, and then this one area. Okay, that is normally multiply the sorry, minus the columns. Okay, now as I am going to discuss about the beams. Here's the beam. So first of all, as I'm going in the x direction, you have to neglect for a while about y direction. Okay, that is this direction, this direction, this direction. Okay, you have to only, first of all, you have to only calculate about the y direction. Okay, here you will see very easily that here is the beam is given, that is 4, and how much your beam is located. Okay, your beam is must be located from this column to this column. Okay, that is from this column to this column. Okay, this to this column. Okay, therefore you have to detect the cover from this side and come from this side. Okay, as whenever I go and open my sum of the statement here, that is base shear calculation here. Okay, now you will see here that is number of bays in x direction 7, number of bays in y direction 4. Okay, 5 bays with 4 and one has 6 and other has 10 meter. Okay, that is your bay. Okay, story height that is normally you can see here is not 3 meter, that is 3.5. Okay, thickness of slab is 6 inch, size of beam there, and secondly now size of column is here. Okay, this one your size of column, that is 600 multiplied by 600. Okay, this is your column height. Okay, now remember that this one is your column, and you can see here that this one is your 4 feet into the horizontal direction. Then you have to detect the clear cover from half from this side and half from this side. Okay, let's suppose you can say here that this is our column, and you have to detect if normally you have to detect the half from this side and half from the other side. Okay, so I'm going to start my calculations. That is 4, right here 4 minus. Okay, that is 600 here and 600 total here. So this is total 600. Okay, this is total 600. So 600 divided by 2. Okay, how much? 300. It means that this is 300. This one, this distance from this distance, and this distance from this distance is also 300. Okay, that is divided by 2. Okay, Why this is 300 and this is 300, okay? So 300 divided by this is mm, you have to divide this into meter, okay? That is 0.3 from this side and 0.3 from this side, okay? So we can write here 4 minus 0.3 minus 0.3, okay? So how much you get? You get normally 3.4. You can multiply with this 2, that is 0.6 minus 4, okay? You will get 3.4, okay? I normally do it from the back, but it is in positive, okay? That is 3.4. What is this 3.4? This is one beam length, okay? One beam length. You can give it name into the meters. Now you have to count that how many beams of 4 meter, okay? That is 1 beam, 2 beam, 3 beam, 4 beam, 5 beam, 6, 7, 8, 9, 10, and so on, okay? Up to this, okay? Whenever you find here, then you will find out that is normally 20 beams, 20. One beam has length is 3.4, okay? And multiply its thickness. Always remember that multiply its thickness means that you are going to multiply with its width, okay? What is basically width? That is 400 meter and 200 mm, okay? That is 200 mm is normally width. Always remember that whenever you take the dimension of the beam, you can also do it the preliminary design for the beam, okay? That is the span that is normally divided by 12 to divide by 15, okay? That is normally you can design it, okay? For the drop panel, okay? You can easily preliminary design it, okay? But it is not as such preliminary design. I just take the dimension randomly, okay? Remember that that is 400 mm to 200 mm, okay? So I take the normally normal section, okay? That is 400 mm 200. So you will take here about 200 mm. Here you can see there 200 mm, 200 divided by, so how much? That is 0.2, okay? So you can write here that multiply by 0.2, that is the thickness. So how much you get? Whenever you calculate it, you will find different things like uh, what will you get here? 20 multiplied by 3.4 here, okay? That is multiplied by 0.2, okay? You will find here 13.6 normally, okay? 13.6 right here, that is square and meter, okay? This one. Now other I again go to my map, okay? And now I will, first of all, I will find out my 6, okay? Now what is number 6, okay? Basically number 6 dimensions, okay? You will see here that is 1, 2 and 3, okay? That is normally 3 beams, that is normally in your into the horizontal direction, that is normally 3, okay? That is 1, that is 2, and that is 3, okay? That is normally in 3 directions, 1, 2 and 3. So again open your chart here. Always remember that maybe your column size may be different, it's up to you. So 6 minus, again same process, like the column dimension is 0.3 and column dimension is 0.3, so minus 0.3 and minus 0.3, okay? So equal to, so how much you get? That is 5.7, okay? You can write here 5.7, that is length of one beam regarding 6 meters. Now you have to first of all calculate that how many beams you have 6, that is 1, 2 and 3, okay? So you can write here 3 multiply its length, that is 5.7. I just copy it to save my time, and multiply with what? Multiply with thickness, okay? So as you know that what is the thickness of the beam, as I calculated earlier, that is 0.2. I will actually copy it to save my time, equal to, so how much dimension you have to get here? 3, that is multiplied by 5.7, that is 5.7, okay? Sorry, 3 multiplied by 5.7, this one, and multiplied by 0.2. Okay, this one. So how much you get? You will get about 3.4. Okay, that is again that is normally, if we calculate, is 6 minus 0.3 minus 0.3. Okay, sorry, 6 minus 0.3 minus 0.3. Okay, how much you get? That is 5.4. That is normally, I have done some mistake, that is 5.4 here. You can write here 5.4. Okay, now when I go multiply with 3 and multiply with 0.2, then you will get it 3.24. Okay, 3.24 meter square. This is normally now what is basically a third beam. Okay, this is normally your shear wall. Okay, and you can also provide here, let's suppose this is your shear wall, but you can also provide here, let's suppose here you can producing the beam here. Okay, that is normally the beam. Okay, so this is here we will provide the beam here, then you can easily provide the beam. Here I am providing the beam, that is you can provide here that how much, that is normally 10. Okay, that is normally 10 minus 0.3 and minus 0.3. Okay, so how much you can get it, and minus 0.3 minus 0.3. Okay, so how much, that is 9.4. 9.4, that is length. So how much, that is only one, that is in so you can say that that is normally shear wall, and if you are providing the beam here there upon the shear wall, it is normally only one. So you can write here 1 multiplied by 9.4. I am going to save my time. Multiply by 0.2. Okay, this one, and equal to this. So this one, always remember that the shear wall is normally acting as your long column. Okay, the wall that is normally called as the shear wall, that is normally acting as your column if you are providing the shear wall under your beams. Okay, so this is normally acting as the long column. Now you are 1 cross 9.4 multiplied by 0.2, you will get your beam value. And that is 1.88. 1.88. Okay, you can write here square meter. Now first of all you have to go the add here. So total, how much total here you will you have to calculate this all. Let that is meter square, not the square. Okay, that is 13.6. you have to multiply with this, that is, sorry, first of all you have to take this value. Yes, that is 13.6, then 3.24, 13.6, 3.24 and 1.88. 3.6 plus 3.24 plus 1.88. So that is normally you get total 15.72 meter, and this one is the square. Okay, now always remember that this is beam in, this was beam in x direction. Okay, so whereas for the slab you can also take, you can take normally internal values. Okay, for the slab, but try to take the whole values. Okay, to cover all this. For the slab, you have to take the mid of the grid of the column. Okay, this one. So that is one beam is 3.4. So this one is your in x direction. Now I'm going to take other, that is beam in y direction. Okay, you have to take the dimension of the slab from grids, from the center of the grid. Okay, that is from the center of the column, because your slab is normally localized and placed into the center of the grid. Okay, now other thing that we normally take, that is beam. That is normally what is beam, that is in y direction. Sorry, I think so forget one thing more, that is you can see that in the x direction, that is normally applied here a secondary beam. Okay, so how we apply here secondary beam. Okay, now here you can, if it is secondary beam, as I already told you that dimension of the secondary beam is always less than that of the primary beam. Okay, what is primary beam and what is secondary beam? Primary beam is that beam that is normally occurred on from the column to column, and the secondary beam is always lies from one beam to the other beam. Okay, and your secondary beam is always have the pin support. Okay, and the pin support, there is two reactions, that is one is vertical and the other is horizontal. What is basically cause the pin support, and why we normally apply the pin here? It is because we applied the pin here because whenever the load occurred not due to this beam and convert into this beam. Okay, so main load is occurred on this beam, then distribute it here, and then go to the columns and then drag into the ground, and then to the and drag into the foundation, then into the ground. Okay, so here primary secondary beam. So here first of all we have to calculate the length, as we know that the secondary beam having length is normally 10. Okay, this one is your basically secondary beam. Okay, this one, so you can write here 10. So now how much you will do minus. Okay, now if I open this statement here, then you will see here that that secondary beam is 320 and 180 having thickness. Okay, this one is the thickness of your secondary beam. Okay, so here if you see that this is normally size of beam, that is 400 mm and 200 mm. Okay, so it means that uh, that 400 it is normally at the depth, and 200 is normally at the width. Okay, so as we are watching here, okay, if we normally see here, let's suppose I have draw a, there is lemma, that is if you here 0, that is REC here. Okay, this one is 1 and other is REC here, and other is 1 CO here, C here, that is this one. Okay, now here if we say that the beam that is lie here, this one. Okay, now you have also to detect the total clear cover. Let's see, why not working? CO inter that is, I select this inter, that is inter. Okay, now as you see that I am finding for the secondary beam. Now that this time this is not a column. Okay, this time its dimension is how much? Width. Now we will see the width of the primary beam. So how much width is primary beam? That is normally 200 mm. Okay, so that is 200 means 0.2 on this side, that is normally 200, and you can see here there is normally 200 mm. Okay, so 200 mm from this side, that is total width. Okay, so whenever you're gonna open this, you will find here that is normally 200 mm. Okay, so you have to find out the minimum cover here and the minimum. So you have to deduct here these both. You have to deduct this here. You can find this here. You can deduct here. Then you will find here. Okay, that is, you can find out here. That is 200 minus how much? That is 200 divided by 2. Okay, this one. It means that you have to 100 here and your 100 mm here. Okay, so how much? That is normally divided by 1000. 0.1. Okay, so you have to minus 0.1 from here and 0.1 from here. 10 minus 0.1 minus 0.1. Okay, so how much you get? Whenever you do this, you will get the value at 10 minus 0.1 minus 0.1. Okay, normally you will find here 9.8. Okay, 9.8. So first of all, when you find here 9.8 here, that is your length. Now what is you have to find out the total depth. Okay, so why we that is normally 1, that is secondary beam, multiplied by 9.8. I have to save my time here. Control C, Control V, multiply by what? This one. So here you will see that what is basically the thickness of your secondary beam. Okay, open this value, open this, and you will find here the thickness. Okay, this one is the thickness. Okay, 180 mm. That is 180, sorry, 180. That is, you will get that 0.18. Okay, that is 0.18, and here you will write here 0.18 very easily. So how much you get when you do this multiplication here? Then you will see that 9.8 multiplied by, okay, how much you got here? That is 1.764. 1.764. Okay, 1.764 cubic meters. That is, we can say that is meter square. Okay, that is meter square. Now what about the beam in y direction? Okay, now I have already calculated it, that beam in y direction. What is basically beam in y direction? Open your ears and you will see here. There is 1 beam, 2 beam, 3 beam, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, this one beam here, and 20, 21, and this one is 22, and this one is 24. Okay, why normally is provide the secondary beam? Okay, so we normally provide the secondary beam is order to give the support, because in the middle there is large bending moment, as yeah, because due to the large panel we have to increase the thickness of the slab. In order to reduce the thickness of the slab, we normally provide the secondary beam. Okay, so this is for the base calculation for the seismic shear. Now we are what we are doing. Okay, so here now base in y direction. Okay, so how many base in y direction? That is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and 17. Okay, there is 17 base having the same. Okay, so first of all, here I have already calculated, so I will not waste my time. I will write here fast. Okay, 4 minus 0.3 minus 0.3. Okay, so how much you get? How much you get here? That is 3.4 here. Okay, now there is 2. That is, this one is 2. That is, this one is 2. This one is 2. Okay, so 2 minus how much? That is same. That is 0.3 minus 0.3. Okay, Always remember that one thing more, that when you are doing a y direction, okay, that is this one, in this direction, it means that you are resisting the wind load or the seismic load on toward the y-axis, calculating this. Okay, so you have to worry, and you have to first of all calculate that. So you have to minus this value and this value. When you are going this, you are minus to the width, but you are going the y direction, then you have to minus the depth. Okay, you have to minus the depth. Now what is depth? Basically you have to minus this area, this one. Okay, can you see my mouse? That is this area, and you have to come here, and you have to minus normally this area, means this area. Okay, this area you have to minus this, then you will come here. Same as if you want to find the slab, like not from the grids. Okay, sometimes not from the grids, you have to detect the column here, then you have to find from here to here, that is one method. And when you are going towards the right, okay, then from here to here. Okay, this one. But here you have to take from the grid to grid. Okay, so now other thing is, but always remember that you have to that is grids, from grids to grids. Okay, here I have find the slab from grids to grids. Now 2 minus 0 0.3, 0 0.3, that is 1.4. Okay, I will find out the length very fast, because other is 10.5 minus 0.3 minus 0.3. okay, this one. And how much you get? That is 1.4. okay, this one. And other thing is this, sorry, it is 9.4. okay, that is 9.4 length. Okay, this one is R is length, this one, this one, this one, and this one is length. Okay, now other length, that is 6 minus 0.3, that is length of shear wall, minus 0.3 minus 0.3. okay, how much you get? That is 5.4. that is normally length. Okay, so first of all, here you have to first of all calculate what you have to first of all normally calculate here, that is 17, because your number of column in y direction is 17. okay, so 17 multiplied by 3.4, and that is multiplied by 0.2. 1. okay, because there is normal thickness, it will give you 11.56 square meter. Okay, that is one side. And other thing is normally what, that is a 2 cross 1.4. okay, that is the other thing is, that is this one, 2 cross, that is I'm going to this calculation. okay, 2 cross 1.4, and multiply with what, multiply with thickness. okay, 0.2. how much you get here? You get here, that is 0.56 square meter. okay, sorry, square meter. okay, this one is this value, and the other one is this value. okay, so this is normally a simple calculations. So it is a it is second thing. So what is basically third thing is, that is 2 multiply by, okay, now you have to calculate, this is 9.9. okay, so what is basically you will first of all find out that what is basically 9.9. this is not actually you will find here that if we normally find that is 9.9 here came. If you find out here, that is 10.5 minus 0.3 minus 0.3. okay, you will find out 9.9. okay, so 2 multiplied by 9.9. what is why 9.9 and why 2? Because you will see here that is normally 2 direction in the y-axis, that is one beam, and that is in other beam, that is 10.5, and that is also 10.5, 2.9, and that is in 0.2. okay, so what will you get? So you get here 3.96, 3.96, and you can write here meter and square. So, okay, so now there is normally three values you get here. So 11.56, other one is 0.56, and third one. So you can write here 11.56 plus 0.56 plus 3.96. Okay, 3.96. Okay, so how much you normally get here? That is 18.24. 18.24 meters square. If you don't believe that, then you can calculate here 11.56 plus 0.56 and plus 3.96 plus 3.96. Okay, this one, that is 16. Oops, sorry, that is I forgot one thing. Okay, that is normally I have to also calculate one thing more. Okay, that is I have to calculate one thing more. Okay, actually I forgot one thing. Okay, what I basically forgot, I forgot these two walls. Okay, this wall I basically forget. Okay, that is shear wall, that is normally upper at the beam, and we imagine that this is normally lies below the beam. Okay, and this one is this wall. So here you can write here enter multiply by what how much, that is normally 6. Okay, you can write here about the 6 and minus 0.3 minus 0.3. Okay, how much you get? 6 minus 0.3, 0.3. So you get the 6 minus 0.3 minus 0.3. Okay, you get here 5.4. Normally shear wall normally lies and sometimes worked as a long column. Okay, but you can also provide the shear wall, then you can also provide into the basement the shear wall, then onto the shear wall you can also provide the plain beam. Okay, you can also consider it as the plain beam, and you will also provide the shear wall into the lift. Okay, it is normally used to resist the lateral force adjacent to the ground. Okay, that is normally shear walls, and that is 5.4. Now how much shear wall? That is 2 shear walls in this direction, that is 2 multiplied by 5.4 multiplied by 0.2. Okay, so how much it will came? 2 multiplied by 5.4, that is multiplied by 0.2. Okay, this one, so 2.16, and you can add here 2.16. Okay, I'm going good. 2.16. Okay, that's one. As I told you that I have some calculated some values, but 11.56. Okay, plus 0.56. Okay, plus 3.96. Okay, and plus 2.16. Okay, we are 18.24. Okay, this one, now it is good. So this one is our beam value in y direction, and this is one our beam area in our beam area in our x direction. Okay, that is in x direction 18.72, and this is normally in y direction. Okay, now we are going towards walls. Now first of all, always remember that where you have calculate some beams. Okay, like you have calculate a beam here, this one. Okay, you have calculated beam here, you have calculated beam here, here. Okay, so under these beams the automatically under beams the walls will also be located. Okay, so you will not take wall from this grid, you have to take wall from start of the column. So for the wall you have to apply the same techniques, that you have to detect this. Okay, you have to take this area for the walls. Okay, so So here for the basically we are now we are going towards the walls. Okay. Whereas before I think so before going towards the walls, we have to calculate first of all columns. Okay, because column is not a big technique, but column is very little technique. Okay, for columns. It is very easy to locate the columns. Okay, it is very easy to locate the column. How you will find out the columns? Okay, first of all, count the number of columns. That is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 and so on. Okay, and up to this. Okay, this one. Okay, after adding all the columns, all those columns given you in the drawing. Okay, so first of all, after covering all those columns, you will have this is normally given you the length, this now will take you the width. Okay, and you can take the half of the column, because you have to lumped here. Okay, this one is lumped, half of the this side, half this side, then lumped into this here, half this side, then lumped onto the ground level of this. Okay, so as you are going and you are finding out the columns, you have to deduct it, that is 600 cross 600. So first of all, you have to find out the number of columns, count the number of columns. So as we know that number of columns, so number of column is equal to 30. Okay, that is number of column is equal to 30. This one is normally show you about number of columns, that is normally give you 30, and that is numbers, and how much about the length and width, that is normally show you square meter, that is 30 multiplied by, you can see here 0.6, because 600 sorry 0.6 and multiply by 0.6. Okay, so what will you get here? That is 30 multiplied by 0.6 multiplied by 0.6. Okay, so that is 10.8. Okay, 10.8 meters square. Meters square. Whereas our UBC code 107 says that if I open my code here, and here I'm gonna check about reduction of load here. If I search here reduction of load here, then you will see here that here this one. Okay, this one is our this. So this is UBC code says that the live load reduction shall not exceed 40% in garages. Okay, so whenever we use the garage, okay, having the capacity per 9 vehicle, okay, then we have does not exceed, okay, the reduction more than 40%. Whereas the for storage having exceed 5 kilonewton per meter, having 100 psf load. Okay, it means that we also not take any reduction if there is more than 5 kilonewton load. Okay, no reduction shall be made, except that design live load on column may be reduced by 20%. Okay, so if that column, if there is live load is on column, but if there is storage load having 5 kilonewton load per square meter is normally acting on the storage, okay, then no will be reduction on the storage. But whereas the columns, okay, when we normally applied load, that is normally applied axial load on the column, then we can reduce it up to 20%. But we normally not go toward the 20%. Okay, we normally follow our some techniques. Okay, and we go to the 525 here, this one 22 and this one 25. Okay, whereas we follow this technique. Okay, this code says that the seismic dead load W is total applicable portion of the dead load in a storage warehouses occupancies. Okay, a minimum of 25% of load live load shall be applicable. Okay, it means that that we only allow 25% for the storage load. Okay, where partition load is used for full grind a load not less than 0.50. Okay, whereas for the partition load, if normally we added the floor design, okay, this is normally also for the access of the roof, or that we cannot take the roof as a zero, because here maybe some access anywhere there is some chance that you have to go on the roof and you have to adjust some work, then you have also give some factor of safety. Okay, that is the load intensity factor for the partition load is 0.5, but we normally give it 1. Okay, so I will also show you that why we give it 1. Okay, is an snow load here that is 1.50, that is not in our area. Okay, but where in the area we have to take the design load that is 30 psf, okay, or less. Okay, not need to be included where design load snow load exceed 1.50, the design snow load should be included. Okay, then if there is the load having 1 point in the, like suppose there is no area and having load less than 1.50, then we will not include it, but having load increase 1.50, then we will normally give the here design load. Okay, whereas some other factors. Okay, we have to take that what our load, what our code is said. Okay, if I open 5-4 here, that is normally, that is not CQ, that is if there is for the soil. Okay, that is when we find when the that is it's component of the structure here. There is 5-4. There is wind speed. Okay, that is normally found the gust factors. Okay, that is for the code for the gust factor, that it is normally different things. Here is the CE 5-4. I am going toward the 5-4. Okay. Oh, so UBC code is normally we follow because of ACI. Because ACI we follow ACI and UBC code both. So snow load here, wind load here. So here you will see here that if we open this one 5/4 here, 5-4, this one. Yes, go open here. With this one. I think so. That is we have to follow this. So this one. Okay, this one is well as given that floor shall be designed for unit live load set as forth in table 5.1. These loads shall be taken as minimum live load. Okay, in kilonewton per square meter or pound. However, center projection is used in the design of building for the occupancies listed, and load at least equal shall be assumed for uses not listed in this session, but that creates or accommodates similar loading, where it can be determined in designing floor that the actual live load will be greater than the value shown in the table. Okay, so where it can be determined designing floor. Okay, it is determined that if actual load is greater than the value of shown table 5.1, the actual load shall be used in the design of such building or portion thereof. Okay, it means that the loads which is normally show you in table 5.1. Okay, that is if there is load is there is some less load than the load you are going to be designed, then you will be applicable or you will be applied for the different load. Otherwise you have to occupy and you are okay with that value. And other factor that is normally that is this given to you, that does design live load as set as for this table 5.1 for floor and table 5.3 method 2. Okay, for roof may be reduced on any member supporting more than 150 square foot. Okay, let's suppose you have any member like a slab, beam, or anything that is normally covered more than 14 square feet or 150 square feet, including flat slabs. Okay, except for floors. Okay, then you have to apply this formula, that is r into a into minus 14. Okay, but normally what we normally follow the storage weight, that is normally we detect the 25%. Okay, of the total rate. And must remember that rate of reduction of equal to 0.08% for floor, and for roof that is 5.3 for roof. So what is basically for roof, that is from 0.8 to 0.8 to 40. Okay, that is for the point factor for the roof. Okay, so for the columns, that is I show you for the columns that for the load having greater than 5 kilonewton, we can reduce the column load up to how much percent? That is normally up to 20%. Okay. So now we are going to design the walls here. Okay. Walls. Falls in x direction. Okay, because you have to find out in both direction, because first of all, whenever you are opening the SAP 2000, you have to find the load in x direction as also in y direction. Okay, eqx and eqy, because your earthquake maybe happened in two direction, that is in x direction or maybe in y direction. Okay, so you have to calculate the wall into the x direction and then into the y direction, and you will also give the base shear also in two direction, that is in the x direction and also in the y direction. Okay, so the values you are calculating for the building are the same. You have to give the values in the x direction the same as you are giving the value to the y direction. Okay, or you are giving to the value to the y direction is same as you are giving the value to the x direction. Okay, now we are going walls in x directions. Okay, that is your walls. Okay, that is one wall, two wall, three wall, four wall, 5, 6, 7, 8. This is your from wall to wall. Okay, now again I have written some factor, that is 4 minus 0.3 minus 0.3. Okay, other one is horizontal, that is 6 minus 0.3 minus 0.3. Okay, that is other factor. Third one is your what, that is you are, if you are comfortable, that is 3. What is 3? That is first of all you have to calculate the weight. Okay, that is 6 minus you have to calculate with, that is 3.4 1 equal to, that is what thing is go together, there is 5.4 here. Okay, that is other thing, that is normally is your length. Okay, so how many walls that you have in 3.4 direction? Okay, whenever you count this 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 and 20. Okay, so there 20 number of walls. Okay, so you have to write here 20 multiply by number I have here, and here you multiply with what, and here you have to multiply with the wall thickness. Okay, what is wall thickness? That is 9 inch. 9 inch in whenever you convert to the 9 inch, that is 9 inch divided by 12, you have to convert it to the foot, and when you divide it with 3.28, that is number going to into this one, multiply by, oh sorry, 9 divided by 12. Okay, this one converted into foot. Okay, now divided by 3.28. I think so there is some mistake here. That is 9 inch. Okay, now you have to convert the 9 inch. Okay, that is 9 divided by 12. Okay, that is normally in the foot. Now 1 foot, now multiply by 3.28, that is into the you can see here that it is normally converted into the meter. Okay, so this is a normally you can find out here why it is not happening. It must be having, that is 9 divided by 12. Okay, it must be happened that 9 divided by 12. Okay, one thing, so yes, that is right, that is 228, that is 230 mm. Okay, so if we say that that is 230 mm divided by 1000, you will get it about 0.23. 0.23. Okay, now first of all, what value you will get from it when you do it multiply with this, then you will get 15.64. Okay, 15.64 square meter. Any kind of building. Okay, you don't you don't have to any hesitate here. You can find out from the calculation, not from the software. Okay, it's now up to you. It's up to your choice now that how you will calculate here. Now here, how much x-axis value, that is normally 1, 2 and 3 values. Okay, that is 3 multiplied by 5.4 and multiply by what, that is a 3 multiplied by 5.4 and multiply by 0.23. Okay, this one. So from this calculation what you get, that is 3.726. okay, that is meter and that is square meter. Okay, this one, this so these two value from you get here, and you have to calculate these both, that is 15.64 plus 3.726. okay, 77.6. okay, so whenever you calculate these two values, you will get what you get, 15.64 plus 3.726. okay, this one. So this is normally we get 19.366. 19.366. okay, this one. Now what about your shear wall? Shear wall. Shear wall calculation. So first of all, for calculating shear wall, you have to first of all say that this beam that is normally under this, the shear wall is provided. Okay, first of all, how much shear wall, that is normally 10 minus same 0, shear wall is normally at the column. Okay, that is shear wall minus, okay, 0.3 minus 0.3. okay, so you will get what you get here, 9.4. okay, that is 9.4 meter. okay, sorry, 9.4 meter. Now you can say that how many shear wall, that is one shear wall multiply by 9.4 and multiply by thickness of shear wall is taken 0.2. why 0.2? Because when I open my code and I come to the chapter number 9, chapter number 9, page number 45. This one. okay, now what it normally provided, that now you will see here that number 45 here, number 45, this one, you will find out here very easily that shear wall, where is shear wall, okay, that is you will find here, okay, that is shear wall is 1 second, that is 9.9, 9.8, that is 9, and basically you will find here 9 and 49 page. okay, this one. So here you will see that a minimum 2 parallel shear walls should be placed in each orthogonal directions. okay, the walls to be categorized, shear wall having minimum thickness is 200 mm, that is 8 inch. The height of the thickness ratio, that is h by t, and length thickness ratio l by h shall conform to given value in the table, that is 9.14 table. okay, So whereas this one is a quote from the UBC that asks you to take the 200 thickness. Whereas whenever you visit the code, that is whenever I visit the ACI 318, that is American Constitute code, it says that minimum thickness is 6 inch 150 for walls up to 2-story height. Okay, it means that that as we take as our story, that it is one ground floor, first floor and second floor. So for up to this floor means up to this one. This one we have to required 150 thickness. Okay, uh, the minimum thickness is increased 1 inch 25. Okay, which means that after 7.6 meter. Okay, that is for each 25 foot. For each 25 foot, which means that let's suppose that is 150 and you are going 25 foot upward, then you have to increase the thickness, that is normally 1 inch, that is 25 below 2 stories. Okay, the code requires a horizontal and vertical reinforcement not less than this one and this one. For walls more than 10-inch thick, there should be reinforcement for each direction placed in 2 layers parallel with the faces of the wall. Okay, the minimum bar size was limited, this one as not more than this. Okay, so for walls more than 10 inch thick, okay, having wall more than 10, then you should reinforce for each direction, place in 2 layers parallel with the face of the wall. Okay, this one is for the grade. Okay, the layers places and grades 50 and 60 should not be less than 30 and 36 bar diameter. This one for the 10 inch thick. Okay, first of all you have to focus only size. So here this is given 150 but but we can also follow ACI or UBC. Okay, whereas UBC there says that is 200 so I am taking here thickness is 0.2 okay, so equal to, if you take here, that is what will you get here, that is 1.88. If you do this multiply here 9.4 1.8, okay, that is 1.88 meters. Okay, that is meter up to meter square. Okay, this one is for shear wall. Okay, this one is also meter and square. Don't forget to put the unit. Don't forget to put that is 10.8 meters square. Don't forget to put the unit. Okay, this one. Now we are going to basically discuss that we are now we are going to give the walls in y direction. Okay. So first of all you have to give basically walls in y direction. So how you will give the walls in y direction, having the same method. Okay, this one, and open the drawing here, then you will see that is 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19, and this one is your y direction. This one, this wall, this wall, this wall, this wall, this wall, this is all your in y direction. Okay, so 4 minus 0.3 minus 0.3 same 0.03, sorry, that is 0.3. okay, equal to, you will get 1, other is 2 is minus 0.3 minus 0.3 equal to, okay, other one, and you will when you convert this, that is 10.5 minus 0.3 minus 0.3. What is basically 4? That is 4 is normally given. This one is 4. This is 4. Okay, this is 4. That is 2. This one is 2. This one is 2, and this one is 2. These two are, that is 2, and what is basically 10.5. This is 10.5, and this is 10.5. I am taking 1 10.5. Then I will take 1, and that is 2. Then I will multiply with 2. I am taking 1 2, then 1 and 2. Then I will multiply with this 2, and this all with, that is 1 2 3 4 5 6. And that is number of walls. I will multiply with all, then I will get that total wall. Okay, in y direction. So the next technique is you have to find out the each areas. Okay, that is but you will get that is 3.4. I still remember that when you get is 2.34, 2.34, that is 1.4. Remember that it is normal in your meter, okay? That is 1.9. That is three things, okay? You find very easily. That is three things. So now, how many walls you have in x direction? Whenever you find out the walls in y direction, that is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is basically your walls, okay? This is basically your wall in y direction, okay? This one is your wall. So that is 17 multiplied by 8.4 and multiply by what? Multiply by 0.23. That is wall of thickness. It's now shear wall. Remember that this is wall of thickness, okay? 17 multiplied by 3.4 multiplied by 0.23, okay? So you will get this, how much? That is 13.294. 13.294, that is square meter. That is meters and that is square, okay? One this one and other is that is two walls, as I already told you that that is one and that is two, okay? Two walls, that is 2 multiplied by how much? 1.4 and other is multiplied with 0.23. As I told you that you have to take the meter square, okay? So 1.4 multiplied by 2 and multiplied by 0.23, okay? Then you get that 0.644. That is normally 0.644. 0.644, okay? That is meter, and you have to get this into square, okay? This one. What is normally other things, okay? 0.644, and other thing is that is there is two. There is how many walls of 10.5? You can say that there's two walls, as I told you, one wall and other wall, okay? So that is 2 and multiply with this, how much? That is 9.9, okay? That is multiplied with 0.23, okay? 0.23, okay? This one, how much value you will get? That is you will get the value 4.554, okay? 4 point meter and that of the square, okay? So you wanna add all this, okay? This one I'm gonna copy with this to save my time. You have to copy with this to save my time, and you will gonna copy with this to save my time, okay? Equal to, now you will calculate this. Whenever you calculate this value, you will get 18.492. 18. So if you want that, I will calculate for you. Plus that is 4.554, 4.554 plus 13.294, 13.294, okay? So equal to, that is 18.492, okay? As I told you earlier, 18.492, okay? Meter, and this one square meter, okay? So this is basically the wall, okay? Now other thing, if you want, okay, let's suppose. So another thing is that as I told you that there is some walls, but let's suppose if you have considered that there is some opening, okay? Let's suppose you have a wall here, and let's suppose you consider that there is a window, there is other window, there is other window, and there is window, there is window, and there is door. Then you have must to detect the for the exterior walls not more than 45%, and for the interior walls, that is we call as that the partition walls, okay? You have to give it your own also having, that is our normally our partition walls that normally given to our washrooms and other things, 4.5, but you also include that of the partition wall except the exterior walls. These all your exterior walls, okay? And this is your interior wall, this wall, this wall, this wall, this wall, this wall, this wall, and all these walls. This is basically your interior walls, okay? This is your exterior walls, this one and this one, and this, there is no exterior wall, okay? In this bay, okay? This one is all bay, this is not exterior wall, okay? For the exterior wall, that is normally some partition, okay? Where is for the, if you open the UPC code in 97, this one is You can see here that is given 99.59. This is not table. This is for clay and this is for 9.59. Yes, this is the table. Okay. Now here you can first of all, this is actually the table what if I open the duplicate tab, okay, and sorry, if I open the duplicate tab, not a new tab, and I came down here and if I open this, then if you see here, then it is show that minimum to there's 200 and height to thickness ratio and length height to L by H confirm the values in game table 9.14. okay, this was your table basically, 9.14 table. Okay, masonry load, if seismic bands, then that is height to thickness ratio is 12 and length to height ratio is 0.4. okay, this is one is factor. That is for seismic zone 1, that is that length to height factor may be reduced up to 20%. okay, this is normally your factor. okay, as I show you that ACI code says that if there is height is more than 25 foot, then you have to increase the 1 inch. okay, this is normally height to thickness ratio. okay, that is normally how much height is increased. okay, if there is, let's suppose, 10 foot increase, then you will also provide this thickness. okay, and this is length to height ratio, that let's suppose that if you are, how much length will be increased and then how much your height will be done. okay, this one. So basically what is the purpose of show you the table again? This is for this purpose, that deduction. okay, let's suppose you have a walls here, as we have walls, and let's suppose we are show here that there is all windows. okay, that is, this door consists of windows, this is consists of windows, this consists of windows, this is ventilator. okay, this is not window. okay, then you will follow this. okay, for total length, and there is size of opening in bearing walls. okay, one story for one story building, and if you are working in zone 2B and zone 2A. okay, as I am from Dera Ismail Khan, okay, Muhammad Walid, so my zone is 2A. okay, and one story building, that is 0.60, two story building 0.50, and 3 or 4 story building, we have to detect the 0.42. what is basically 0.42? okay, this is 0.42 is actually the area of the total. okay, of the total area of the basically height. Let's suppose our wall is 10 cross 10. okay, this one, so I have to detect only 42%, not more than this. okay, 42 divided by 100. okay, so I have to take only 42 square foot area. okay, which means that in 100 wall I have to take only 42 square foot area. okay, this is for the zoning. Now whereas if we follow the direct technique, then what does she say that what the code says about door and window. If we follow direct opening, then you can see here it says that makes all door and window opening in a wall simultaneously as far possible when brick working is in progress. okay, it says that try that whenever your brick is progress, it means that your work of the building is going on, then try that at that time you have to provide the opening. Otherwise, if you can't provide the opening that time, then you can provide as far as possible. okay, here it shows that keep opening in external walls not more than 45%. okay, this one is your external walls. If you see that, in short words, we can say that boundary wall, this one, this one, this one, this one, this one, basically which covered the building. okay, which covered your building is normally shows you this is your exterior walls, and this one is your this one, this is all your interior walls. okay, so this shows that if your exterior was not more than 45%. okay, but our code says that if you are 3 or 4 story building, then you are go about 0.42. okay, that is 0.42 normal, but this shows that you are not going about 45% of the area of walls, where an opening internal wall should not be more than 30% of the area of the wall. okay, it means that for internal wall you could not detect the area more than 30% of the wall. okay, keep remember that. Keep remember this technique, that for the area having an internal wall having more than that is 30%. okay, this shows that for zone 1 and zone 2 there is okay, that you are comfortable, that you can go up to 0.42. for zone 2B, that is 0.37, and for zone 4 and 5, that is 0.33. okay, keep remember that for zone 3 and 4, we normally take SMRF, okay, seismic resistant frame we normally take, and whereas for 2A and 2B we normally take IMRF, okay. For 2A and 2B we normally take IMRF, okay. I will show you that what is SMRF and as it is basically IMRF, okay. So this is normally opening. I can also add a note here that you can provide let's suppose if you can detect opening, okay. If you want to detect, then you can normally detect opening. You can detect opening up to 30%. Okay. Also it's for all, okay. This is a not basically codependent 30%, okay. This is the not, this is for all, that is for the opening you have to detect the total area of the wall, that is interior wall, about 30%, okay. All the countries normally applying this technique, okay. Don't be worried about it. Now first of all I am going to calculate about the what is basically floor finish load, okay. What is basically floor, now we are applying here floor finish load, okay. Load calculation, if we apply here load calculation, okay. So there are two methods for finding the finding the basically the floor finish load, okay. For the floor finish load, if you have applying the load of the marble or the tiles, then you have to apply again the same process like a length, you will take the length and width, okay. There is two things, or length cross thickness, okay. Length cross thickness, you can take the length cross thickness. Normally we take the thickness of the floor is how much, that is 6 inch of slab, that is depth, and normally we take up 3 inch, okay. That is if we normally convert it into 3 and divided by 12 bit, okay, and then more into divided by 12, okay. Oh sorry, 3.28 and then multiply by 100,000, okay. That's only 76 mm, okay. So for the floor finish you can take normally it depend upon the design or drawing, we normally take 60 mm, 50 mm, 60 mm, okay. For this you can easily take if you are for the floor finish, you can take the length and the width and the thickness, okay. It will give you in kilonewton, it normally give you in kilonewton per meter cube, okay. And then first of all you have to find out the unit weight of the marble. If you want to give the unit weight of the marble, then you can also apply the unit weight of the marble, then it will be okay for you. But if let's suppose your code, if you have a code and it give you some factor, okay, like I will here floor finish load, okay. Here some example, that floor finish load, and I'm going to my UBC code, and here if I partition load, okay, this one, there is some picture what I open is, you can also take this 5.6.2, okay, that is 5.6.2 here, 5.6.2, where is 5.6.2, 5.4, 5.6, 5.6.2. That is very difficult to find out basically. Sorry for that. So this is basically SMRF, okay. Moment resisting frame expression detail to provide ductile behavior, okay. That is give the detail about ductile behavior, okay. Keep remember this is SMRF. So first of all we have to find out partition load, okay. Partition load, we will now find that, I will direct it right here, partition load, okay. That is normally, I hope so I will find here very easily, partition load, okay. So floor in office buildings and other buildings where partition location are subjected to change shell design to support in addition, okay, all other loads. A uniformly distributed load, dead load equal to 1 kilonewton per square meter of floor area, okay. This one access floor system, that is the floor system that you have access, it means that where you can reach very easily shall be designed to support in addition all other loads. A uniformly distributed dead load not less than 0.5 kN per square meter. Okay, it means that axis floor system, it means that the floor system you have any axis, okay, you can go very easily, then you have to support in addition to other loads, and that is dead load not less than how much, that is 0.59 kilometer of floor area. Okay, that is normally you have to take 0.5 kilonewton per square meter. Okay, that is 10.5 psf for floor area. So we it means that we have also provide air how much, that is we have also provided the factor, that is 1. So what does mean that of the floor area? Okay, it means that floor area, if I open my project here, then you will see here that normally we consider the roof as a floor. Okay, here is the floor, office, and all the other floor we have to calculate here. Okay, so first of all we have to find out that where the floor will be occurred. Okay, so the floor will not into 3 columns. So for the floor we have to also find out the internal dimensions. Okay, this dimension, internal dimension and internal dimension. Okay, as for the slab, but keep remember that we have to take the same dimension for the floor as for the we have take for the slab. Okay, so again I open my sheet here, and floor finish load, that was I go to the open, and first of all I will check here that what was the dimension of my slab. So that is 417 square meter. I will come down, and that is we take here 417. Okay, that is meter and square meter. One thing, multiply with what does code says? Code says that access floor system shall be designed to support in addition all other uniform distributed load not less than 0.5 Newton per square meter of floor area. It means that our floor area is this one, 470 meter square, multiply by what? Multiply by 1. That is factor. Not less than 0.5. Okay, it means that I can take more than 0.51 because it is not limit to the upward, only for restroom. Okay, only for guest room, because for the restroom you will take only 2.4, not exceed 2.4. Okay, so this one is kilonewton per meter square. Okay, so for this one and this one cut. Okay, so only kilonewton will left. Okay, so sorry for that, this one, sorry for this. Okay, so it means that I'm going to work gap. Okay, it means that this one and this one cut, then how much remaining? Then only 417 kilonewton is gonna be remaining. Okay, this one I'm going to color the value because to make safe from the confusion, because it is basically it will make me confused. Okay, wall in y direction, that is shear wall. This one, that is air wall. This one, okay, this one wall in x direction. Hope so, I'm going good. That is 10.8. That is this one, 18.424. Okay, this one 18.24, wall in y direction. Secondary beam, this one, that is total 18.72. This one, and we go to the upward beam in x direction, that is beam in secondary beam. That is good, and that is other criteria. Okay, file, save, and SAP engineer valid, and I'm going to convert here that project file. Okay, now our file is gonna save, and now I'm okay with this. So while other thing, what is basically other thing is you have to make the table. Okay, you have to make the table area. You have to first of all make the table. This one. So you need here table design here, and layout and references, the mailing. That is 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Download. 1, 2, 3, 4, 5, 6, 7. Okay. That is okay. Sorry for the late. Okay, that is now we have easily calculate here. That is first of all you have to calculate here S number. I have to reduce its size. In fact, that is 14. That is element. Oops, still it's large. I have to change it. That is 14. That is element. Okay, and other is basically SAP done the same calculation like this. Okay, they have taken the values from the UBC, or you have a code of other code like ACI, ASC7, ASTM, IS, Indian code, every kind of code. SAP is already calculated because they have. Okay, now area. Oh, there is normally changes size. Don't know why. That is area. Okay, I'm comfortable with this. That is meter square. This one. That is thickness. Okay. Now the thickness you can calculate into 14. That is 14. Other is volume. That is 14. This one is meter. This one is meter cube. Sorry, meter cube. Okay. Unit weight. Okay, this one, and unit weight. Okay, how much unit weight? That is kilonewton per meter cube. Okay, this one. And what is basically last is weight in kilonewton. Okay, you can say that dead load. And this load, that is dead load, and so what is this? So that is dead load, and that is normally 14, and you can say that kilonewton. So okay, so this is basically the load, our load, what we have to calculate here. Okay, first of all I can insert the table here. That is insert in column, insert to the right, to the left. Notes, I don't want this. I don't want only insert on propose. Sorry, that is what is happening to it. You can also do this. Control copy and insert this, insert rows below. This one, okay, and with that insert rows below. Okay, this one, and insert rows below. Okay, this one. So first of all, we have to calculate that is 1. What is element? That is slab. Okay, that is slab. 1 is slab. That is, we have to change its. Don't know why it's can't change its shape. Don't know this change shape. Okay, 15 SB. Okay, I will check it. I will check it after that. Okay. So control A, then I will convert into 14. So it will work now. Yes, it is good now. So slab. So first of all, you have to find out the area of the slab. As I so come here, and you will see here that is 417 square meter. Okay. Breakdown, that is 417 meters square. Okay, this one. And come to the thickness here. Normally, you know that where we provide the slab thickness is 6 inch. Okay, so 6 divided by 12. Okay, this one is 0.5 and divided by 3.28. That is 0.5 and multiply by that is 152. Okay, so you have to provide here that is 150 mm. So in 3 meters, so 0.15 equal to here you will see here that there is some that is how much dead load onto your building here. So 417 that is and multiply by 0.5. Okay, this one is meter. Keep remember this. Don't forget this. Multiply by 0.15. Okay, this one you will get the 62.55. Okay, 62.55. This one is meter and this one is meter cube. Now other thing is basically your unit weight, that what kind of unit weight you are going to be applied here. So for the unit weight, you come here back here and open this back here and set complete by yeah, you will find here PCS unit weight one. Okay, this one. So this is first of all your open unit weight brick. Okay, so here brick is broken. If broken brick, common brick, but here you will see here that there is the cement concrete plane. Okay, that is for plane for 2400 kilogram per meter cube, but cement concrete reinforced means that also cement concrete having some steel. Okay, having reinforced, so that is density is normally 100 more. Okay, so 2500 kilogram per meter cube. Here we will apply here 2500 divided by 100. Okay, so that's 25 kilonewton per meter cube. Okay, this one that is 25 kilonewton per meter cube. Okay, so open this open this and then you will write here 25 kilonewton dash meter cube. Okay, or per meter cube. Now you will see here that this meter cube will cut with this meter cube. Okay, and you will get the required kilonewton on the your building, that is 62.55 multiplied by 25, that is 1563.75. Okay, 1563.75. Okay, this one what is this one is all calculation what I have done normally for the base shear. Okay, so what is the other parameter? Other parameter that was you have to find here, you have to go upward and you have to find the other parameter that was actually the beam. Okay, that was beam in x direction and the other beam is in your secondary beam also you have to add here. First of all, you have beam in x direction. Okay, that is beam. So beam. Okay, how much area for the beam? That is normally slab and beam 9.4 total 18.72. Okay, this one is your total area for the beam, 18.72. Okay, that is meter square. Now what is the depth of the beam? Okay, first of all open your question here and you have to find the depth of the beam, that is 400 mm. It means that 0.4 meter. You can write here 0.4 meter. Okay, so how much you get here, that is 18.72 multiplied by 0.4. Okay, so you will get here 7.488. Okay, that is meter cube. 7.488, that is called meter and cube. Okay, so how much for the beam? Okay, for the beam you have to again take how much, 25 kilonewton per meter cube. Okay, so I think so I write somewhere else. Okay, so you have to write here kilonewton per meter cube. Okay, so you have to kind of that is this meter cube is cut with this meter cube. Okay, So you have to get the same value as I show you concept here. What only left here, 7.488 multiplied by, okay, so 187.2, 187.2 kilonewton. What is basically 3? Before going to the 3, you have to write here secondary beam. Secondary beam. Okay. Now again, go to the up here and find out that what is your basically secondary beam 1.764. This is your secondary beam. Always remember that beyond the partition load, you can also find out any type of load if you have found the load intensity. Okay, if you find the load intensity of anything, okay, like the roof life load, we have take 0.4 kN per meter square. The roof, you have also live intensity. We have also live intensity of the snow load. Okay, let's suppose you have applying the snow load here, then you will also provide here that is less than 30 psf. Okay, now you can easily say that you can easily see here that the 20 psf also written here. Okay, now here area of the secondary beam is normally how much? That is 1.782. This one, that is 1.764. Okay, sorry for my mistake, 1.764. And what about its depth? Okay, if you gonna open this, then that is 320. It means 0.32. 0.32. Okay, 320 divided by 9. Okay, that is 0.32. Okay, so apply here 0.32, that is meter square, that is meter, that is how much, multiplied by 1.764. okay, that is equal to how much? That is, you will get there 0.5648. okay, 0.56448, 0.56448. okay, this one. And reinforced having same, kilonewton per meter cube, okay, equal to what? Meter cube. Okay, this one. And 0.56 m multiplied with 25. Okay, 25, 14.112, 14.112. okay, 14.112. okay, that was. Now what is basically third? This is beam in, this is normally in x direction. Now normally you can say that the beam in y direction. Okay, now what is if we say that beam in y direction, that what will basically the area? Okay, that we, if we come here and we see here that beam in y direction 18.24, 18.24 meter square. Okay, that is meter square, that is one. Okay, that is meter square. And the what is depth? That is 0.4, having same depth. Okay, meter, sorry, 0.4 meter. Okay, equal to how much you get? 18.24 multiplied by 0.4. okay, 0.4. so how much you get? That is 7.296. 18.24, okay, that is 18.24 multiplied, that is 7.296, 7.296, that is meter cube. Now what is for beam? Having same, that is kilonewton per meter cube. Okay, so what is the value you get? This meter cube cancel with this, so multiply by 25. It is 182.4. okay, for beam in y direction, 182.4, 182.4. okay, that is kilonewton. This is also kilonewton. Okay, 4. Now what is your 4? That is column, I think so. Columns, that is, we can say that it's column. So for any kind of measure structure, you can calculate easily for this column. For column is that's area is 10.8. I remember that it is 10.8. Calculate 10.8 meter square. And now there is some technique to Res is basically column. Okay, now here is a technique you have to you must have to remember that, as I already told you, for finding the seismic weight of the building, okay, you have to take of the half weight of the column and slab. Okay, you have to take half of the column and the slab. Okay, always remember that. Sorry, column and walls. Okay, you have to take these of the half. As when we open my let's suppose I open my drawing here, then you will see that if we normally calculate here lump mass for the ground floor. Okay, this one. Okay, this one, what is the basically method for finding the lumped mass here? There is the lumped mass here. Okay, this one. So I have to take here, that is L line, this line, that is first line here, this line length here, then I will take the half of this. Okay, half of this, then other I will take the sorry, half of this. Okay, then I will take. So for the lump mass, always remember that you have to take the half of this value. Okay, this is not the half, sorry, that you have to take half of this one. Okay, this one, half of this value, half of this value. Okay, then you have to lump here, then you will get the value you will write before this, same as that is column. So this value, and you have to get these two value add here, and then you will get this value and then lump here. Same as for the second floor, how you will find second floor? Here you will find out the value and take the center. This is center. Now you can take this value, that is normally you can know that the height is 3.5 here given. So 3.5. Okay, so 3.5 divided by 2. Okay, how much you get? That is 1.75. This one is 1.75. Okay, and plus 1.75. So how much you get? That is, sorry, 1.75 plus 1.75. Okay, so that is 3.5. Okay, so you have to lump here. Okay, so there are different types of walls. Okay, for the ground floor, you have to take the half of the basement story, that is seismic basement, and half of the first floor. Okay, for the first floor, whereas must remember in this all tutorial I did not take the top roof. Okay, for the top roof you have to take the half. Okay, let's suppose here this one and this one. Okay, this one. So for the fourth floor you have to take the half of the third floor height plus b, this one, and when you do this a plus b, then you will get this value. Whereas for the top floor you have to, only this floor is going to be left for this value, that is normally you have to take 1.75. Okay, you have don't deduct with anything, or you have don't need to subtract with anything, because it is top floor. Okay, and you have to do this as its own. It means that you have to do this separately. Okay, I do not consider a top roof. I did only for the fourth floor. I did not take the top roof because it will take more time for our topic. So so here I do my topic short, so I basically lumped this. So as I am going to take out the column here, so I, for the column here, let's suppose these are going column and I am on the ground floor, so this value is here, that is a, that is b, and then lumped into the center. Okay, so that is 10.8, and what is basically lumped into the center here, that is 1.75 and 1.75. Okay, this one 1.75. Okay, that is, and plus 1.75. Okay, you will get the middle value. So how much you get? These are meter. 10.8. Okay, multiply by 1.75 plus 1.5, that is 3.5. Okay, 3.5. Okay, 1.8 into 3.5, that is 37.8. You can write here 37.8 meter cube. Okay, so for the column, keep remember that for the column you have also have the same value. Okay, for the column you have the same value, that is 25 Newton meter cube. So how much you get? It is multiplied by 25, 945. Okay, 945 kilonewton. Number 5. Now for walls, always remember that for any kind of seismic load or seismic loading or lumped mass, you have to do this technique. Okay, half of this story, and lump both, means A plus B, you will get this value. Then half of this story, and this both lumped, and those will get the center of the story. Okay, keep remember this. This technique. Okay, now for wall. Now if we say that wall in x direction, So again, go back and you will see that you will get the value, that is 19.366. I will go here for the wall. If I forget, then I don't want any mistake here, because at this point 19.366, this one. Okay, 19.366. Again, as the wall, because it is for the columns, again the wall has the same concept, because if you are doing, that is half on lumped on this side, half lumped on this side, then this A plus B, then if you are only finding the ground floor, then you can find out here. As I consider that all the floors are symmetrical, okay, so for the ground floor you have to take half of this story and half of this story. Okay, this one. And so 1.75 plus 1.75. So remember one thing, that your wall always, this is your wall, okay, and this one is going your beam. Okay, so this one is your beam and this one is your wall is going. Always remember that you always detect the wall with the depth of the beam. Okay, this one your depth of the beam. So if I show you this section, okay, this one is your wall, this one is wall, okay, this one is wall, this one is wall is going, let's suppose, and this one your beam. So what is your depth of the beam? Open this and you will see here that your depth of the beam is 400, that is 0.4. So you have to deduct minus 0.4. Okay, so how much you get from it? You will get easily, that is 3.5 minus 0.4. Okay, how much that is? 3.1 multiplied by 19.36, 19.366. okay, so that is 60.0346, 60.0346, this one, and this one is also meter square. So now first of all, there is wall. Okay, it's depends up to you that what kind of wall you are gonna be make. Okay, here if you open your unit weight, that is brick broken, brick common, cement ordinary, cement, that is your type of rock. Okay, here I am going to make the wall of the brick common. Okay, that is 1600 kilogram per meter cube. Okay, this value. So I will convert this into Newton. That is normally give us 16. Okay, so I write here 16 kilonewton per meter cube. Okay, so how much you get this? That is 60.0346, 60.0346. Okay, multiply with 16. Okay, multiply with 16. You get 960.5536. Okay, 960.5536. Okay, that is 960 kilonewton all. Now I am going about the 6. What is 6? Basically that is shear wall. You go for it and you will, first of all you have to find the area of the shear wall. That's 1.88 meter square. You write here 1.888 meter square. Okay, this one is basically for the shear wall in x direction. Okay, 1.88 meter square. And you know that what is that is 1.8 1.888 basically meter square. That is for basically shear wall. Okay, and you know that what is the height? Same. That is, if we copy this and we're going to paste this. This is equal to 1.88 multiplied by 3.1. Okay, 5.828. 5.828. Okay, that is meter cube, and here you can 5.828 okay, 5 meter cube here, then equal to, that is 25. Remember that for the shear wall you have to consider that as 25. Okay, that is 25 equal to multiply by 25, 145.7 145.7 kilonewton. Okay, this one. Now number 7 item, that is wall and into y direction. Okay, here you have to write. So 18.492 is a given direction. You can see here that is 18.492. Yes, that is 18.492. 18.492. This one, and that is normally 18.492. Okay. Basically, I think so. That is normally wall in y direction. Okay, I think so. I forget here one thing, that is in x direction we have normally forget to apply shear wall. This one is shear wall. Okay, this one we have to apply a shear wall. Okay, this shear wall and this shear wall, that is two shear wall. So 6 minus 0.3 minus 0.3. Okay, that is normally we get 5.4. Okay, now for after getting the 5.4, you have two walls, multiply by 5.4 and multiply with 5.4 and multiply with 0.2. Okay, so how much you get is, that is 2 multiplied by 5.4 multiplied by 0.2. Okay, that is 2.16. 2.16. Now it is good. Now it is going right. Okay, for the shear wall, for the beams, okay, you have to deduct the basically column. Okay, half of the column. Now 18.492, that is again wall. Again you are talking about the wall. So for the wall, as I told you that you have to take the lambda of the same, that is you have to control C, control V. Okay, for the wall in y direction you have to apply the same technique. Okay, now here what will the 18.492 and multiply by 3.1. Okay, then how much that is 57.3252. 57.3252. Okay, 32 and 52. Okay, meter cube. This one is meter square, this one is meter, this one is meter cube, and how much, that is wall and 16, because we are using common brick construction. Okay, and the common brick construction has 16 kilonewton per meter square. Okay, so 57 multiplied by 16, 917 point. Okay, so here we can provide here 917 kilonewton. Okay, 917 point something. Okay, kilonewton. Always remember that you have to always apply after the point. Okay, that is 19.72, then you have to apply the 19.72, not 1917. Okay, so here I will provide 8, that is what is in the final, that is 8. So here I will apply shear wall. What is basically shear wall? Okay, this one is shear wall, this one is shear wall. I have to add this, that is 2.16. this one meter square, because this one is thickness 2.16. Okay, so you have to apply here 2.16 meter square. So what is basically thing that is you have to apply the same thing even downward. You have to detect the tip of the beam if it is applied. Otherwise your shear wall is actually as a long column. Okay, so meter equal to 2.16 okay, multiply by how much, that is 3.1 6.696. okay, 6.696 okay, meter cube, 6.696 meter cube. Okay, that is 25, and how much you get, multiply by 25, 167.4. okay, 167.4 kilonewton. And here I'm gonna add here, first of all I'm gonna insert here, insert row below, and I will again insert row below, insert. Okay, now total. What is basically total dead load on the building? Okay, when we gonna add all these, then I will get normally about how much, that is uh, I think so I forgot one load, 9 1, that is floor finish load. Okay, what I apply in the last, this one is 417 kilonewton. Okay, you have to apply this, you have to don't need to detect anything. Okay, because it is already in kilonewton, 417 kilonewton. Okay, that is normally factor. So here you can write here total seismic dead load of building. What? Total seismic dead load of building. Okay, whenever you do this, you will get about let us check me, let me check that 1563.2 plus 187.2 plus 114.112 14.112 plus 182.4 plus 945 plus 945. Okay, plus 960 okay, plus and 145.7 okay, plus 917 plus 167.4 okay, this one, and plus 417. So that is load 5499.012. okay, 5499.012. okay, that is kilonewton. This is your total dead load. Okay, so I am going to save this. This is your total dead load. Now you have to do some calculations. Okay, here as you know that what is basically your seismic weight of the building. Okay, seismic weight of the building is that is dead load plus live load. Okay, this one is plus live load. Okay, so this one given is your dead load, this one is your dead load of your given table. Now I am going to apply some of the your live load. Okay, that is applicable. So for the live load, first of all I wanna take for the live load, there is some other class that I will take. Okay, tomorrow inshallah. Okay, so first of all I will make only table for the dead load. Okay, that is the table for the dead load. Before going to the dead load, I will first of all I will make you understand here that what is basically dead load. Okay, chapter number 5, page number 45. I will open is page number 45. Okay, this one is the reduction factor for the roof 0.08 to 40. What I am talking to you. Okay, that is for the flat roof. Okay, that is the basically tributary area in square meter. Okay, that is tributary area is actually that is the area having from one span to the another span. Okay, that is one span to the another span, then that span to the other span. Okay, that is known as the your tributary related area. Okay, keep remember this. That is five. Yes, this one table. Okay, now this one is actually table. What this table show you, this is basically the load what is normally applicable on the building. Okay, this one is the access floor system. That of the access floor system is actually that of the floor system what we can easily reach or which is in our approach. Okay, but is accessible. Okay, this is for access floor system. Okay, you can see here that office use or computer use. Okay, in our building you can see here that is our building. This one is office, this one is office, this one is office. Okay, this one is office, and this one is library, this one is library, this one is library, classroom, classroom, classroom. Okay, now first of all we there is some office. Okay, for calculating the live load we have to take the area, all the area of this. Okay, as you know that the area in square meter. Okay, so what our code says about this. So code normally tell us that if we open this 525 page, I will open the duplicate here. I will open the duplicate here. I will go to the 525, 5 and page number 25. Okay, this one actually map of NWFP, JK and northern areas. Okay, that is zone A, zone 2B, and basically this is a map of Pakistan, that is Punjab, Islamabad, Rawalpindi, Chakwal, Khushab, Jhelum. So that is Sindh, and this one is the seismic zones. Okay, this one is the map of Pakistan. Okay, seismic map zoning of Pakistan. Okay, this one is the seismic map zoning of Pakistan. So you can see here that I have to open first of all 525, this one. Here what choice basically this one this code give to us, what kind of choice this code give to us. Okay, here you can see here that is a 525 page has been opened before us. This one. Okay, this one seismic load, that is W, dead load. Okay, I have already calculated you that is the total dead load and applicable portion of the load listed below. In storage and warehouse occupancies, it means that storage or warehouse occupancies minimum 25% of floor live load shall be applicable. Okay, that is means that floor live load is shall be applicable of 25%. Okay, where the partition load is used in the floor design is 0.50 as we calculate earlier. And you know that here the snow load factor is also given, that is 1.50. Okay, but 25% is the percent, it is basically not the factor. Okay, this is one thing that we have to calculate normally 25%. Okay, whereas in the IS code, that is Indian code 2002, it says that if there is some value that is less than 3 kilonewton, then we have to calculate this 25%, but it is more than 50%. So for sorry, if it is more than 3 kilonewton, then we have to take that of the value of 50%. But here you can say that here is factor of safety that we have to take about 25% value. Okay. So open this and now calculation of live load. According to UBC 97. Okay, this one. I think so. It's enough. We will discuss it into the our next class. Okay. Thank you.